Once again, thank you very much to the organizers. What I'm going to speak about is the following. So for Lie algebroids, there are two notions of morphism. One is known as Lie algebroid morphism, and the other is known as Lie algebroid comorphism. And both were introduced by Higgins Mackenzie. And well, obviously, then two notions. The natural question is which one is better and which one is more natural. Actually, well, the correct answer is both, but applied to different situations. And comorphisms, as particulars argued by Alberto Catania, that's very, how to say, natural in the context of Poisson geometry. So they're related to Poisson maps, so there is a certain duality under two functorial constructions, which I will recall. And what is done here? So we introduce a new notion, which is, well, kind of similar, generalization of comorphism to the L infinity context. So for L infinity algebroids, and it turned out it's not entirely obvious. So because we actually have two slightly different versions of this notion. One is more complicated, one that is more obvious, and we're able to generalize these known relations for Lie algebroids and Poisson manifolds to the case of L infinity algebroids and P infinity manifolds. And this is a joint work with my student Sam Brady, which is in progress. Well, it's almost done, but there are various details to be worked out. So let me remind general nonsense, so to say. So what does comorphism for fiber bundles? Actually, just for fiber bundles or vector bundles in particular, different people depend on different, well, needs according to the problem. So they consider two notions of morphism. One simply is a just, well, square, commutative square, and well, it's at the top here, right? And but unfortunately, this notion allows to pull back functions on total spaces, but not sections. And a competing parallel notion, which some people still call morphism, still not comorphism, looks more complicated, but it actually is completely symmetric if one properly looks at the first notion. So one can decompose this commutative square into kind of diagram of pullback related with a pullback bundle, where the arrow at the top is identical on the fibers, right? And then all information about the morphism itself, as far as the total spaces are considered, so is in the in this arrow where you have a mapping of the fixed base. A fiber bundle mapping from a given fiber bundle to pullback bundle. And now if you view morphisms of fiber bundles this way, then comorphism will be exactly the same, but now the role of pullback and the other bundle is reversed. You have a mapping from a pullback bundle, right? Now one may argue which well, directional arrows one should pick, and in the literature people pick different directions. Incidentally, for example, of applications, because this allows to pull back, to have a mapping of sections. Well, I said pullback, actually push forward in my convention. And say in the book Gugimin Sternberg, Geometric Asymptotics, this exactly is defined to be the proper notion of morphisms of vector bundles, exactly because we work with pseudo-differential operators acting on sections vector bundles and the need functoriality for sections, right? And of course, the second is done purely algebraically, just for models. There's an algo for models over different algebras. Okay, so this is kind of well known, but it's good to recall. And then now, again, the fact that may be regarded as folklore was clearly put down by Higgins in Higgins Mackenzie work in 1993. That if you do this for vector bundles, by passing to the dual bundle, you can convert morphisms to comorphisms and comorphisms to morphisms, well, the opposite direction. In opposite direction, in my convention of arrows. Some other people take other convention, then it will be just the same direction. But I'm sticking to the idea that you simplest example is vector spaces, and for vector space you pass to the dual space, and then arrows are reversed. Okay, and now they introduce fundamental notion, this Lie algebraic comorphism. Now, a comorphism vector bundles is a Lie algebraic comorphism if first it preserves the brackets, homomorphism of Lie algebras, and also there is a relation for anchors. So if you have a section and you take the push forward of your section, then to every section corresponds a vector field with applying the anchor, and this vector fields must be related or intertwined by the map of the bases. Okay, and again, this can be done entirely algebraically, and this I think was established by Hübschmann, right? And if you want to compare with Lie algebraic morphisms, then it is not so easy to do it in terms of sections, but it's the easiest way to do it in terms of supergeometry. Then you can consider the corresponding vector bundles with reverse parity, and then they're defined by homological vector fields, and then Lie algebraic morphism is a Q-map. One also can, of course, explain the notion of comorphism in terms of homological vector fields. This will be done later, in the more general context, when I will give the L infinity version. Okay, why comorphisms is also important? Because actions, actually, I explained in terms of comorphism. Action of a Lie algebroid on something is a comorphism into the tangent algebroid. Right, actually, to the section corresponds vector fields, which infinitesimal generators of your action. Like, okay, and now there are two fundamental theorems, simple but fundamental theorems, which establish relation between Lie algebroid comorphisms and Poisson geometry. First of all, remember that every Lie algebroid can be viewed in different manifestations, so to say, structure and sections. Lie Poisson bracket on the dual bundle, and Lie Houghton, it means odd Poisson bracket on the anti-dual, parity reversed dual, right? And all structures, everything what you can do should be possible to be formulated in all these manifestations, right? And so if you have a vector bundle comorphism over Lie algebroids, if it is Lie algebroid comorphism, then the dual vector bundle morphism will be Poisson map, and actually if and only if, and conversely the same. And the same for Lie Houghton brackets on the anti-duals. So this is one fundamental relation. Another fundamental relation is that if you have just Poisson manifolds, then we know that it was actually in one of the earlier talks, one of the equivalent structures for a Poisson structure on M is a Cazul bracket on differential forms, which is one of the manifestations of the cotangent Lie algebroid, right? And again, so if I have a morphism of Poisson manifolds, so that means map that pull back preserves brackets, then the corresponding cotangent, then they have cotangent comorphism. And this cotangent comorphism turns out to be a Lie algebroid comorphism, right? In particular, in one of the manifestations, that means the pullback of differential forms will preserve Cazul brackets. Okay, and now our task is to convert everything to L infinity world, right? Or infinity, whatever world. Let's recall the notion of L infinity algebroid. So it's, again, I'm using convention where L infinity algebroid is a direct generalization of Lie algebroid. So therefore, the brackets are alternating parities and antisymmetric. So it is a vector bundle, which you may think in the super world. So everything are super manifolds. If needed, you may also assume some Z gradient, which may be independent on Z2 gradient, but for science, we need only Z2. And so we have a structure infinite algebra on sections, and also there are infinite sequence of high analysis of anchors, which are important for, for the Leibniz rule. So if you multiply section by function, you have a Leibniz rule where a high anchor, and particular anchor with many arguments pops up. And this everything can be encoded in a single piece of structure, namely homological vector field, which lives on the total space with a reverse parity. And odd squares to 0, and if you expanded its formal vector field, and you can expand it with respect to natural degree, z degree, which is given by the linear structure in the vector bundle. So you have pieces, well, you have 3 pieces written here. Actually, there's no high pieces. There are low order pieces. And in one of the previous talks, with this 2 early low order pieces, well, correspond to curvature or whatever. It is very, sometimes it is convenient to assume that you don't have low order pieces at all. So you start from just this third term here, which corresponds to just a Lie algebraic structure plus high order, well, homotopy, extra things. And tilde means parity. So the standard, I'm sticking, its notation was introduced by Manin years ago. So when we have superworld, Z2 gradient is called parity, is denoted by tilde or the object instead of this modulus or whatever. Yeah.
Thank you. Is the anchor an L-infinity morphism?
Yes. Well, if you assemble, yes. Yes. Yeah. Okay. Yes. The quick answer is yes. Yes. So, and a nice way of seeing this, you can assemble all high anchors into a single map, which is a nonlinear map from pi a or pi a1 more precisely to pi tm, and this is a Q map. So it commutes with homological vector fields. Right, and so now, well, you anticipated my next slide. Because I haven't told you what is L-infinity morphism. L-infinity morphism is exactly in this language is the Q map. So we describe L-infinity algebroids as a Q manifolds, and say you have a mapping of Q manifolds and which intertwines corresponding homological vector fields, right? And well, this is spelled out here. So if we have, if you write this in coordinates, so this is a linear part. Well, it's the essential thing starts from quadratic part. So this is like first homotopy, extra homotopy term, and this formulas tell you exactly what these functions should satisfy to be Q morphism, and that means L-infinity. Okay. Now we're going to compare. We're going to introduce the notion of comorphism and compare these equations with what we'll get there. Right. So suppose again we have 2 L-infinity algebroids, and suppose we're given a vector bundle comorphism. So that means one mapping is one arrow goes in the opposite direction, right? So in coordinates, well, you see what is easiest to understand. So you have a map over the basis, which goes in incidentally the opposite direction, and then the map on fibers you see instead of x, which was before, now you have y, and that exactly corresponds. You have a map from the pullback bundle, not to pullback bundle, from not to. And now there is a theorem which generalizes a known statement, which I think due to Mackenzie or maybe partly folklore, that Lie algebroid comorphism can be explained as having a unique Lie algebroid structure on the induced in the pullback bundle, right? And if we exactly just pull this as a condition, put this as a condition, then but in terms of homological vector fields. So if there's homological vector fields that isn't related with a given vector fields specifying the structure in A and the structure in B, then it is unique, and it is very easy to write down the explicit form of that, and this by definition will be L-infinity comorphism, and this is a generalization of what we have for a Lie algebroid case, and in particular. Examples. For example, it introduces a push forward of sections, which now will be nonlinear, but it's fine because we can expand it, and the Taylor coefficients of the expansion will give you high components of L-infinity map. And the claim is then the push forward of sections will be L-infinity L infinity morphism of a corresponding L infinity algebras. And if you think about L infinity algebras, you need to describe them somehow. And a nice way of describing the corresponding algebra with a homological vector field, which now infinite dimensional, which lives on the total, on the space of sections. So you see this homological vector fields, and using this expression, one can easily prove this claim. And an example, which is, well, I guess is useful for applications, what is action, infinitesimal action of an infinity algebroid of some given manifold or supermanifold. It's an infinity morphism into the tangent, in the tangent bundle, right? And this can be, of course, translated to the sequence, well, of vector fields, which live on our manifolds or supermanifolds and satisfy certain relations. So, and I guess, my guess that physicists knew that long ago without knowing this, the name, right? And in particular situations, this was explored by other people. So I should mention here Marco Zambon, actually, who has a work on L infinity actions of Lie algebroids. And I should say that my own interest to that was prompted by a question asked which Marco asked me, well, some years ago about, well, L infinity actions. And I started to look into that, and this work partly resulted as an answer to his question. Right. Now, how about these fundamental theorems, right? One needs to be careful, because when we in the world of p-infinity manifolds, and p-infinity manifolds are manifolds equipped with a sequence of analogues of Poisson's brackets, of alternating parities, well, then what is a p-infinity map? And p-infinity map is not an ordinary map, as it was one can find. And this is exactly a particular case of a thick morphism, a notion that I just came across some years ago, and this thick morphism is not, as I said, not a point map, right, as physicists would say. So, but rather a relation of the kind very similar to what Alberto Allen and Bernard Derain were with very different motivations were considering. So it's canonical relation between cotangent bundles. But what's important for me, it's described by various particular class of generating functions, which are as close as possible to ordinary maps. And if you have such generalized maps, which are not maps, then you still can have pullback of functions, which is a nonlinear mapping, which is a new thing, which is nonlinear map, nonlinear pullbacks. So I don't have time, so I cannot go into details about that, but this is a very interesting thing. But in ordinary Poisson geometry, one can explain what's the Poisson morphism between Poisson manifolds in two different ways. One is in terms of functions, something that pullback of functions preserves Poisson brackets. And another way is more down to a differential geometric way. So you have a Poisson bivector, which is a tensor field, contravariant tensor field, and then you have two contravariant tensor fields. Then there is no, well, push forward or pullbacks, but then I have 5 minutes. But one can say when they're related. It's generalization of the, well, related or intertwining, being intertwined for vector fields. And then, so one can say that a map is a Poisson map if these contravariant tensor fields are related by this map. Okay, now in the world, but this is very easy to check, these two things are equivalent. Now, in the world of thick morphisms, so it becomes less obvious. So one can define what is p-infinity morphism as a thick morphism, such that the generating function described as thick morphism satisfies, well, certain Hamilton-Jacobi equation, which corresponds to, corresponds to this. In the ordinary case, the relation being intertwined, well, for Poisson tensors to be intertwined. Okay. And then the theorem is that if this relation is satisfied, if it has Hamilton-Jacobi equation, then on the level of functions, you get L infinity morphism between these high Poisson brackets. Okay, so this was done in some other work. So I'm just explaining the background for that. And then the claim is that here again we can have an analog of the classical statement. So we have comorphism of L-infinity algebroids. Then for the dual bundles, you will get P infinity or S infinity for odd version morphisms that gives, in particular, L infinity morphisms on functions. In a way, it's a nonlinear extension from generators of L infinity morphism of sections. Okay, and now, but then there is a second theorem, theorem B, so to say. You are given from Poisson manifolds to algebroids. So you are given P infinity manifolds, and you have cotangent algebroids, L infinity algebroids, and you want from Poisson map, this means P infinity map, get L infinity comorphism. Unfortunately, this doesn't work exactly this way, and we need some further generalization. And this further generalization comes from some technicalities. We need to define. Well, first of all, we need to speak about thick morphisms, and we're speaking about thick morphisms of vector bundles. So for thick morphisms of vector bundles, there's a kind of a notion of linear fiber-wise linearity. Well, this can be described in terms of graded, particular weights. Well, but what's important, linearity means that you have nonlinear mappings, but some say linear functions are preserved. So linear functions are mapped to linear functions in a nonlinear way. This is a bit weird, and so we need to define particular class of thick morphisms, and then the comorphism. Well, particular example of such thick morphisms are given by a tangent morphism correspond to thick morphism. Well, recall what we need all this for. So suppose you have a P infinity map. So this is a thick morphism. So we need to consider tangent, analog of tangent map, which will be again thick morphism, and then want to dualize. And when we dualize, we are supposed to get a comorphism, but not in the previous sense. We get a comorphism in a more general sense, and which is the correct notion. So I had to introduce some steps. And now, so this is the definition. So it is a canonical relation. It again, particular kind of, because time is run out. So it's a particular type of canonical relation between cotangent bundles specified by generating function of a special form, not like for ordinary thick morphism, or different form, different choice, different generating functions differ by choice of independent variables, and this is defined by particular choice of independent variables. And particular ordinary comorphism are described in the ordinary comorphism of vector bundles are described this way. So they're just special case. Okay, and push forward of sections is defined, and which is a nonlinear mapping. Okay, and then the theorem is that there's error reversal isomorphism between two categories of vector bundles with particular class of thick morphism, which are called dualizable, and thick comorphism as errors. And you can look before I pass to the next slide to the relation between generating functions. So they look almost the same. Actually, there are the same up to change of variables, which is given by so-called Mackenzie-Shu transformation. Right. So these are natural identification of cotangent bundles over dual vector bundles. And if you apply that to here, one generating function will translate to another generating function. Okay, and then we happily, one can introduce now, using this notion of comorphism vector bundles, introduce a natural way, what's L infinity map, an infinity version, and then we have the statement. So analog of theorem B. So if I have P infinity morphism of P infinity manifolds, then cotangent comorphism is L infinity comorphism of cotangent L infinity algebroids. Well, in particular, in one of the manifestations, you have high causal brackets which exactly or differential forms which exactly describe this L-infinity cotangent cotangent algebraic structure, and then have P-infinity map, which preserves brackets of functions in L-infinity sense, and then the pullback, nonlinear pullback on differential forms will again preserve in L-infinity sense high causal brackets. And so this is our main statement. And now let me just finish by saying that I want to dedicate this talk to memory of Kirill Mackenzie, who was a great man who just made important fundamental contributions to the theory. A lot of stuff that we described here, and, well, Lie algebroids, Lie groupoids, Poisson, various bracket geometry. And I was like 3 years ago, he passed away, around a little bit less than 3 years ago. And it's a pity that he's not here, so, but let me just commemorate him in my talk. There are questions?
I guess since your L-infinity algebra is not just NQ, right? It's not.
Sorry?
Your L-infinity algebra is not NQ, not
you mean
just NQ.
The corresponding supermanifold is not NQ. In
Not
general,
just,
I don't
right?
assume that. Well, you can restrict to this case, but you don't have to.
Right. So it probably is Z graded. It does not only concentrate on the positive.
First of all, you don't have to assume that Z gradient.
Yeah.
So
if you have
want Z gradient, you may have it, and all the structures can be made working compatible with that. But depending on what gradient you use, you may have two gradients. Right. Incidentally, here we implicitly used in the definition, we used the second Z gradient. So this, when you look at this form of these generating functions, the generating functions have weight 1 in respect to Q. If you see, well, in the first one Q and U, and the second Q mu and pi, and this corresponds to gradients that exists on the cotangent bundle of a vector bundle, right? Because it's a double vector bundle, and you have two gradients. So my idea is that when you need that gradient, you may have several, and you may use it, right? You don't have to tie it with Z2. Does it make sense?
Where is you like? I don't quite understand. But
no,
NQ is an example, right? But you have like a.
No, you see, the two they have different roles. The two parent is responsible for signs, and Z is a counting device, and you may count in different ways.
But they need to be compatible, I think.
They may be compatible in the simplest case. Physicists say with no fermions. So when you have theory without fermions, so then your Z2 comes from Z. But if you have fermions, so you, for example, have differential forms. Well, in the most naive sense, you may have a one form which is even, or two form which is odd, and which naturally pops up if you have fermionic coordinates from the start.
Yeah, I just want to understand your nature.
We can discuss it. Yes.
So there's a question on Zoom by Dima Royenberg.
Yes.
So, Dima.
Yes.
Yeah.
So, hi. So my question. So you mentioned double vector bundles, but here you're talking about something else. So you have kind of like the same class of objects, and then you have two different category structures. And so you have these morphisms which you can compose and they form a category, and then you have comorphisms which likewise form a category. So is there any relation between those two category structures, like a double category? I mean, apart from saying that over the same base, they're the same.
Well, first of all, Dima, they're the same when you restrict to the case of a single with same base and identity on the base. Then
right, apart from that.
That's right?
Yeah.
But as for high categorical structure, I'm completely ignoramus, so I cannot tell anything. But you will have double vector bundles here, because we're talking about cotangents, and as soon as you have vector, you know very well, then you have vector bundle, cotangent will be double vector bundle. That's why you have two gradients.
Right. Well, double vector bundles when you have are constructed by using only vector bundle morphisms and not comorphisms, right? And they do form a double category. Yeah, I'm just wondering if there's like anything like, well, if you can form squares with like horizontal errors being morphisms and vertical comorphisms, let's say, and you can like
Okay, well,
bring them together in some way.
wait a minute. So just morphism will be a square, or rather some high dimensional, well, three-dimensional thing. You have one square, you have another square, you have errors like that, and this is just one morphism. But how you have cells? How do you have cells? Two cells. Well, we don't have time, as I see, so we need to. We can talk with you.
So probably we should stop here. And so we thank Ted again.
Thank